Solutions. Solutions are mixtures, homogeneous mixtures. We're going to cover solutions, their definitions, some properties of solutions, various ways of representing concentrations of solutions. So a solution is a homogeneous mixture. The solution can be liquid, gas, or solid. So some examples of solutions. Stainless steel. It's a metal alloy. All metal alloys are solutions. They're solid solutions. They can contain several metallic elements in various ratios. The various ratios give us the various types of alloys. There's a bunch of stainless steels. What makes it steel that contains iron, and what makes it stainless is a significant quantity of nickel. But there's a variety of other metals in there at a variety of concentrations to give us different types of stainless steels. So being a mixture means that the amount or concentration can be varied. Salt water is a liquid solution, contains solid salt dissolved in it. We can have soda water with gaseous carbon dioxide dissolved into it. We can have martini water with liquid alcohol dissolved into it. Air is a solution of mostly nitrogen, next oxygen, and then traces of argon, carbon dioxide, and water also. So solution is homogeneous mixture. Homogeneous means that the properties are uniform throughout the mixture. The solution, we identify two types of components of a solution. The greatest component generally is going to be called the solvent. Solvent is the greatest component of the solution. And then we have one solvent in a solution, but we're going to have one or many solutes. So solutes are the lesser components in a solution. And example would be coffee. Coffee would have water as a solvent. It's going to have maybe 100 different chemicals in there as solutes, including caffeine, theobromine, theophylline, tannins, and a bunch of whole other things. There's a range of stuff going from the homogeneous mixtures, the solutions, to the heterogeneous mixtures. Heterogeneous, we see obvious changes in properties of the mixture. In homogeneous, we see no changes of properties throughout the mixture. In between that, we'll have colloids and suspensions. So a distinctive feature of colloid is that they scatter light. So they can appear to be milky, cloudy, turbid. They can be clear, but then if you shine a beam of light through them, such as a headlight in a fog, you'll see the beam of light as it's scattering particles, as it scatters off particles in the colloid. Another aspect of colloids is that they are stable and they do not separate upon standing. So what makes a colloid scatter light is that the solute particles are large enough to be on the order of magnitude of light wavelengths. So if the particles are on the order of light wavelengths or larger, they can scatter light. So colloid, the particles are on the order of the wavelength of light, visible light, but not much bigger. If they get too much bigger, then it'll become the next category, a suspension. So the property of scattering light in a solution, a colloidal solution, is called the Tyndall effect. So the Tyndall effect is how we verify that we have a colloid. A beam of light will be visible scattered throughout a colloid. The colloids are stable because of the motion, the standard motion of solutions, materials, fluid materials such as gases or liquids. That random motion is called Brownian motion, and that motion is able to keep the colloidal particles in suspension. So they move the colloidal particles. So if we use light to be able to see a colloidal particle, we'll see it is in constant motion, but it's constant random motion. If the particles get larger, then they will no longer stay in solution. So if a particle will fall out of solution, then we have a suspension. Suspensions can still scatter light. They can be milky, turbid, cloudy. You're not likely to get a good beam scatter going all the way through a solution. Colloidal solution could be clear, and then you'll be able to see a light beam shining through it. A suspension is not likely to be clear. It'll be cloudy and milky. But when we let it stand undisturbed, the particles fall out of solution. This is a distinctive feature of having a suspension. One of the most common solvents that will be seen is water. And we have around the house, of course, many water-based solutions such as vinegar, coffee, tea. A water-based solution is called an aqueous solution. So aqueous solution is a solution with water as a solvent. To form a solution, to solvate a substance into a solution, the intermolecular forces between the solute and solvent should be approximately the same or greater than the solute-solute intermolecular forces or the solvent-solvent intermolecular forces. If the solute-solvent intermolecular forces are smaller, then a solution is not likely to be stable. So we want the solute-solvent intermolecular forces to be approximately the same or greater than the solute-solute or solvent-solvent intermolecular forces. And when we dissolve things into a solution, the solvent molecules tend to form a cage around the solute particles based on the attractive intermolecular forces. So if we have a polar substance and a polar substance, we'll always arrange the molecules such that the positive end is meeting a negative end, the attractive forces. But the solvent cage keeps the solute particles from recombining with each other to form the original compound. When we dissolve ionic compounds prefer to dissolve into polar substances such as water. Ionic compounds tend not to dissolve in nonpolar substances such as gasoline, carbon tetrachloride, hexane, and similar materials. When we dissolve our ionic compounds into a polar liquid, the ionic compound will dissociate, and we're going to generally assume complete dissociation of ionic compounds. We'll find out near the end of this chapter that's not always so, but that is our first assumption, that ionic compounds will completely dissociate. And we'll be needing to know that later on is how to predict how many particles are in solution. So if we dissolve calcium nitrate in solution, we're going to get calcium ions and nitrate ions. So we're going to have 3 times as many ions, 1 calcium, 2 nitrates, as we are of the original calcium nitrate compound. And we will need know how many particles are in solution for a couple of properties of solutions. There are two components, two energy components of all processes, enthalpy and entropy. Enthalpy is the heat of a reaction. So it's how much heat is exchanged as the reaction proceeds. The general spontaneous process, or more spontaneous process, is an exothermic process. This universe likes to go to a low energy state. So exothermic process means that the system is releasing energy, so it's going to a low energy state. But the enthalpy of solution is not the only component. The other main component is the entropy. Entropy is a measure of microstates or possible states. So the more disordered a system appears, the more possible arrangements there are for the system. So the more possible states there are. So things that appear disordered tend to have a high entropy to them. And things that seem orderly, such as crystals, they have a low entropy to them. There's very few ways that we can rearrange that crystal, so it has low energy. So going from two pure substances to a mixture, we are going to be increasing entropy. So the entropy of solution is always going to be positive. There's always going to be an increase for the entropy of solution. The spontaneous direction, the natural spontaneous direction for this universe is to increase entropy. So the normal spontaneous directions are to have an exothermic reaction and an increase in entropy. Well, they don't always go hand in hand. So the combination of those two gives us the Gibbs free energy. So the Gibbs free energy, delta G, will equal enthalpy, delta H, minus T, delta S. And T would be the absolute temperature scale, Kelvin, and delta S is our entropy. So we're going to want a negative delta H, which is exothermic, and a positive delta S for the most spontaneous process. Those combined will give us a negative delta G. So negative delta G is a spontaneous process. In solvation reactions, we're always going to have a positive delta S, but our delta H can be either positive or negative. So we can have an exothermic reaction or an endothermic reaction. And we have examples of those in the drugstore, instant heat packs and instant cold packs, where we mix two things together by breaking the inner package, and the package gets hot or cold. But for the endothermic reaction to be spontaneous, we have to have a large entropy at a large enough temperature that the entropy effect would be larger than the enthalpy effect and still give us a negative free energy. For the heater reaction, to dissolve something, so dissolve salt in water, we have to break the attractive forces between the water molecules. We have to break the attractive forces between the sodium and chloride ions. And then we're going to make water-ion attractive forces. So this combination of attractive forces should be similar to the ones that we are breaking. If a process becomes too endothermic, we don't have enough energy released with the formation of the solvent interaction, then the process will not be spontaneous because we'll end up with a positive delta G.